So now I have the horizontal component and the vertical component of this initial velocity. My horizontal component is constant, and my vertical velocity keeps changing because of the acceleration due to gravity. So if I look at this diagram, what I can see is I have a very large vertical velocity initially. It's going up quickly. As it goes up, it slows down. Acceleration's acting down, and so this vector gets smaller and smaller as the object goes up. At the top of the path, all I have is a 0 vertical velocity. My horizontal velocity is constant. So this vector is the same length as this vector, is the same length as this vector, and this one, because the horizontal velocity is constant. So if I look at this diagram, same platform. Now I have a projectile that I'm going to launch upwards at an angle of 55 degrees. I'm going at my top speed of 60 meters per second. And so now what I want to see is what happens to this projectile. So I'm going to watch the length of those red component vectors, and I'm going to watch the path that my projectile takes. So that horizontal vector stays the same length. My vertical vector initially is going up, and as long gets shorter. As it comes down, that vertical vector gets longer and is pointing down. So I can see the nice uniform spacing of the horizontal component of my velocity, and I can see as the projectile goes up, the distance between, vertical distance between positions gets smaller. As it comes down, again, that vertical distance between spots gets larger. So I have this nice symmetric parabola when I'm launching a projectile from the ground, and the launch height and the land height are the same. So let's take a look at some projectile problems here. Okay, an object is launched at 50 meters per second at an angle of 35 degrees above the horizontal. So now I'm supposed to find the time the object is in the air. How am I going to do that? Well, I do know some information. I'm going to have to break that velocity into a vertical component and a horizontal component in order to find the time. After you've done a few of these, you'll be able to figure out whether it makes more sense to start with the vertical data or the horizontal data to solve your problem. For this particular one, I'm going to start with the vertical because that's what's changing, and that will hopefully give me the most information, on top of which I know one more piece of data vertically. I know the acceleration. So let us identify what we have. I have an acceleration of 9.81 meters per second squared, and that is down. I have initial velocity in the vertical direction of 50 meters per second times the sine of 35 degrees. That gives me 28.7 meters per second. So now I'm going to use one of the kinematics because I have an acceleration of velocity. And if I take a look at the diagram I was just looking at, when my object is at the top of its path, its vertical velocity is 0. So when I look at this problem going up, final velocity in the vertical direction is 0. So I have an initial velocity, 28.7 meters per second in the vertical direction. I have a final velocity in the vertical direction of 0. I have an acceleration, so I can find a time with the kinematic that allows me to use those 4 variables. So final velocity equals acceleration times time plus initial velocity. Final velocity is 0. Acceleration 9.81 meters per second squared times t, that's what I'm looking for. Initial velocity 28.7 meters per second. Now I have to make sure that I get my signs correct here. Acceleration due to Earth's gravitational pull is down. My initial velocity in the vertical direction is up. I have to decide which direction I want to make positive. It doesn't matter. For this one, I'm going to say I like up being positive, so this has to become a negative 9.81. So I go through, I do the math, I solve, and I get the time is 2.93 seconds. But I'm not done because this is just the time it takes to get up. And I want my projectile to come back down. It's not going to hang out at the top of its path. I'm looking for the time it's in the air. It is in the air as it goes up, and it's also in the air as it comes back down. So I'm going to double that time, and I'm going to get my actual answer. And so I get 5.85 seconds. And that is the total amount of time my projectile is in the air. Find the horizontal displacement of the object. Well, I need to find the horizontal velocity. So my initial velocity is the same as my final velocity in the horizontal direction. So my horizontal velocity is going to be 50 meters per second times the cosine of my angle, and I get 41 meters per second. Now I have a time. So my change in position horizontally is going to be my velocity, 41 meters per second, times the total time it's in the air, which is 5.85 seconds. So I do the math, I end up with a horizontal displacement or a range of 240 meters. And finally, let's look at how high this thing goes, the maximum vertical displacement. So that's delta y. It accelerates in the vertical direction, so I have to have acceleration in my equation. I know its initial velocity in the vertical direction. I know how long it takes to go up. I also know that at the top of its path, its velocity vertically is 0. So I'm going to pick a kinematic equation that involves time, initial velocity, and acceleration. So I'm going to use the 1/2 gt squared plus vi in the y direction times t. So 9.81, and it's negative because it's down, is my acceleration in the vertical direction, meters per second squared, time up. Found the time to go up is 2.93 seconds. So I have to square that. I found my initial vertical velocity is 28.7 seconds, and the time again is 2.93. So there are all the numbers I need to find my vertical height change, and what I get is 42.1 meters high is the maximum height of this particular projectile. All right, let's take a look at this one. We've got a car trying to jump across a drawbridge. It's raised to an angle of 40 degrees, so we know an angle. Car leaves the drawbridge at 30 meters per second, so there's a velocity for us. And the road on the other side of the drawbridge is 5 meters below the end of the drawbridge. So our landing height is different from our launching height. So drawing a picture might be helpful. And I would strongly encourage you anytime you're dealing with force problems or vector problems to draw a picture. So here's my drawbridge, and here's the road at the other side. So my car is going to follow this path. It's going to go up a little bit from the end of the drawbridge, and then it's going to come down. And from the top of the drawbridge to the road is 5 meters. That's what our problem tells us. So we have to keep that in mind when we're doing the math. As we did before, we probably want to find the vertical and the horizontal components of our initial velocity. So let's start with that. Vertical component, I have 30 meters per second times the sine of 40 degrees. I get 19.3 meters per second. My horizontal component of velocity is going to be 30 meters per second times the cosine of 40 degrees, and I get 23 meters per second. This is going to be a little bit more challenging because I don't have the same launch and landing height. So one way I can do it is I can plug it into my calculator and graph it and find out the time from the graph, or I can do kinematics in 2 parts. To do that, we're making our diagram a little bit bigger. So first thing I want to do is identify the maximum height of my path, because at that point my vertical velocity is going to be 0. So if I can find the time it takes to get from here to here, then I can also find the time it takes to get from here down to here. So to the top of the path, my final velocity again at that point is in the vertical direction. It's going to be 0. So I know my acceleration due to gravity is 9.81 meters per second squared. It's acting down, and I know my initial velocity is acting up. So I'm going to use the final velocity equals acceleration times time plus initial velocity. So final velocity is 0. I'm going to say up is positive, so it's negative 9.81 times time plus 19.3. So I end up with a time to get to the top, not very long, 1.97 seconds. Getting to the top of the path doesn't help us a whole lot. But what we can do is, since we're dealing with vectors, we can make sure we include the directions and start here and end here, because we know our change in position, we know our acceleration, we know our initial velocity. So another way to do it to get the total time is to use a different kinematic, and the kinematic we would use is a change in vertical position, and we want the acceleration because we're accelerating downward. We know the initial vertical velocity. So we can use this. We know our initial vertical displacement is 5 meters. We know our acceleration is 9.81. We're looking for time. We know our initial velocity is 19.3 meters per second times time. Now, we have to make very sure when we're doing this, we get our directions correct. We chose up to be positive. So our 19.3 meters per second stays positive. Acceleration's acting down, that's negative. I'm going from here to the road. I'm going down, so my 5 meters is negative down. So there's my equation with the correct signs for each of my vector values. I have a quadratic now, so I have to solve it, and I can either graph it and solve it, or if you're interested, we can give you access to the quad form equation to put in your programming section of your calculator, so that when you have quadratic problems, you just pull up the quad form program, punch in the numbers, and you can solve it very quickly. When you solve a quadratic, you get two answers. I expect you to write down both answers anytime you solve a quadratic. Sometimes they're both positive, sometimes one's positive, one's negative, sometimes you have imaginary numbers. So at any rate, we get 4.18 seconds and negative 0.244 seconds. Well, we can't have negative time, so there is our time. So this is the time that our projectile, our car, is in the air totally from when it leaves the drawbridge to when it lands on the road. And the unit we want to make sure we put in, those are seconds. Okay, now we want to find the horizontal displacement of the car. Well, we found the horizontal velocity component, and it's constant. We found the time our projectile, our car, is in the air, so we can find our horizontal displacement by taking our velocity, 23 meters per second, times our time, 4.18 seconds. And the horizontal distance the car travels is 96.1 meters. Okay, so if I'm looking for the vertical displacement of the car relative to the road the car lands on, what the heck does that mean? Well, let's go back up and look at our diagram here. Effectively, what I want is the distance from the top of the path here down to the road. So I want this vertical displacement right there. Okay, great. How am I going to find that? Well, hopefully I remembered that my velocity, vertical velocity, at the apex is 0. So if I start from there and measure down, that's going to make my life easier. My acceleration is 9.81 meters per second squared because I'm on Earth and it's down. The time I'm in the air is simply the total time minus the time it took me to get up. So 4.18 seconds minus, there was a reason we found that vertical time before, 1.97 seconds. So from the top down, I've got 2.21 seconds. So I'm looking for my change in position, acceleration. So there's my equation, time is squared. So I'm looking for delta y. My acceleration is 9.81, so I can put that in. Time is 2.21 squared. My initial velocity is 0, so this term cancels out. That's easy. So now I'm going to just take that and solve for my change in vertical position. And I get 24 meters. So from the height of the parabola to the road it lands on, the car is traveling vertically 24 meters. That's quite a feat.